just gonna erase the board. But you know what? You have to erase these beautiful formulas. It's very sad to say goodbye to them. It's extremely sad. I wish if we could have written that on the wall, that we could keep it forever. But they fire me definitely after. Okay. Okay, guys, now you're just going to start one of the most interesting chapters of the book. This is going to be chapter number 2, which is going to be essentially the dynamics. You remember from... Say what? You know what?
I don't remember.
The dynamics. Okay, no worries. Do you remember what? You had it before?
No, not with the staff.
Okay. Yeah, did you remember from... as you do not remember, you said. From chapter 1, we talked about the kinematics. What kinematics talked about? The kinematics was talking about the motions. Then in kinematics, if you had, for example, an object, which the object was moving around. For example, imagine that this is a particle. Imagine that it has a mass m, and if the particle takes the direction like that and moves around to come into the same mass, I call that initial position,
And final.
Goes to the final position. In the kinematics, you do not take care of the fact that why the direction of the motion is that, what caused the particle or the mass doesn't move, for example, from this direction straight to that direction, and why these curly paths happen. That's the thing which you do not look at that at the kinematics. The only thing which you look at that is that the particle is moving, and you can make a prediction. That's a very crucial word to use. Make a prediction on where the particle is going to be located at a given time t future. How do you do that? You try to write the equation of the motions, and the equation of the motions, what does it do? The equation of the motion comes to relate the position of the moving particle with respect to the time. For example, you remember with the projectile motions, we had 5 different equations, 2 along the x, 2 along the y. At each one, we had one component of the position and also the time. That's all we talk about in the kinematics. But today, we are going to forget partially about the kinematics and say, okay, we accept the fact that the particle may move or it may not. Maybe the particle takes a stationary position with respect to the reference frame which monitors the movements of that body. We say, okay, the particle either moves or either is stationary. By stationary, what do we mean? It's a very, very omnipresent word everywhere. You talk about the stationary. What does it mean, stationary?
Doesn't move.
Something? In physics, it means that if something which doesn't move with respect to its reference frame. Oh, okay. But what do I mean? Something that it doesn't move by respect to its reference frame. Imagine that, for example, it's a little bit digression, but it helps to learn the stuff. Imagine that, for example, you are gonna take the train. Let's say, for example, you are from Toronto.
So,
You want to go to Quebec, for example. Quebec City in Quebec.
yeah.
You are going to take the train, and this is, for example, the wagon which you are in the train, and you are, for example, this is going to be, let me just draw the wagon a little bigger because I need to just put both of you inside the wagon, then I need to draw it a little bit bigger. Imagine that's a wagon, you are moving from Toronto to Quebec for the Christmas. Sean and Jack is in the train.
Yeah.
For example, the train is moving towards that direction. Imagine that that there is no acceleration. This is a constant velocity. It's not. I call that V naught. And also, both of you, there is a table here. This is gonna be Sean, and this is gonna be Jack. I put J S. S for Sean, J for Jack. Okay. Look at that. When the train is moving,
Mm-hmm.
and you are stationary in the train, what is the velocity of the train with respect to you?
Seven.
It's V naught.
Oh.
Mm. But what happens that if you, for example, if in that case, if you imagine that you put your reference frame, you always need a kind of a reference frame because reference frame pinpoints your motion. Your reference frame in the overall picture is attached to what? Is attached to ground. For example, you see, for example, this is the station.
Mm-hmm.
This is the station in, for example, in Ottawa, somewhere along between Toronto and Quebec, and you put the reference frame, you pin it there. You have a hammer, you pin the reference frame there. It means that the reference frame is not moving with you. The reference frame is somewhere, it's stuck, and you're moving with respect to that. And this reference frame pinpoints your motion. When you look at that reference frame, you see that wagon is moving. But if you take that reference frame, remove it from that station, and take it, pin it just inside the wagon. For example, you have a table. This is Sean sitting here. This is Jake sitting on the other side of the table. And there's a table. You're having Starbucks coffee. And you take the reference frame. You put that reference frame on a plate on that, let's say, wagon. Then you see that the reference frame is moving with you. When the train is moving, the reference frame is still there. Huh? What's the difference between these two scenarios? The first scenario, your reference frame was attached to this, and the other scenario, your reference frame, it is on the plate, on the table, which is going to be there. Two scenarios. Scenario one. In scenario one, the wagon is moving with respect to this reference frame. But in scenario number two, what happens there? Scenario number two, it's what? The reference frame is moving with you.
Moving, yeah.
And in that case, the wagon is in a stationary position with respect to you. It seems that the train doesn't move.
Oh.
You knew about that, Physics 11, huh? You knew that out of Physics 11.
Yeah.
Yeah?
Mm-hmm.
And that's essentially what do I mean by the reference frame. Then, depending on how you define your reference frame, you always come to define the motions in different way. Look at that with the same scenario, with the same reality. The reality is what? The reality is that you are moving in a train from Toronto to Quebec. That's a reality.
Yeah.
But depending on how you define your reference frame, your motion is subject to interpretation.
Mm-hmm.
If your reference frame is at the station in Ottawa, it means that your train is moving. But if you put the reference frame on the same train which you are just moving with, it means that the wagon, it doesn't move.
It's stationary, yeah.
That's right. But
It's depends.
if it's me here, or me,
Yeah.
David, or me, I just put my name there. Okay, go back to the first scenario. In the first scenario, the reference frame was here on the station doesn't move itself,
Mm-hmm.
and I'm standing somewhere.
So, yeah.
Are you moving with respect to me?
Yeah. Yes.
No, yes. 50-50 is good that you do not have to fight. Someone says no, someone says yes, 50-50. The votes. Why the train is not moving with respect to me?
The train is moving.
The train is moving.
Yeah, the train is
Because
moving.
if it doesn't matter, you can just take the reference frame, you remove it with a drill from the station, you put it on the top of my head. And you see that still I'm not different than the station. My reference frame is standing there and you're moving. But if your reference frame is inside the train,
Not moving. Not moving. Yeah.
you are not moving with respect to the train, but with respect to me, you are moving. Because our reference frame are different. You see, the reality is one reality. That's the beauty of the physics. The phenomena of the nature, there is one reality behind it. But in terms of how you define your reference frame, you get different interpretation. Huh? That's right. Or, for example, you can, as a real last clarification of that, imagine that idea, a hat, and you bring the reference frame, put on my hat. And I'm just walking also with you with the same velocity, V0. The train is moving at the V0, and I'm just walking like that around with respect to you with the same velocity. Are you moving with respect to me?
No.
No.
Yeah.
How about you, Sean?
No.
No. But for someone who is looking from, let's say, from the moon, for example, it sees the reality is all the movements of two bodies. But based on how we define the reference frame, our interpretation of the same reality becomes different. Isn't that beautiful?
Yeah.
Yeah, take this one. Then when I come to talk about, let's say, we made a digression from our initial point, which it was, I should say, the dynamics. In dynamics is that you say that, okay, I have a reference frame and something is now moving. Like, for example, the train which you and Sean are moving to, Jake and Sean are moving to Quebec. Something is moving. In that case, what do we want to do? We want to, in dynamics, we want to analyze the motion, why the motion happens, what guides the motion, what makes the motion, for example, takes the direction like that. And we have lots of questions, why? Huh? In that case, we may use the equation of the motions, but the thing which is important for us for the dynamics is that to look at the picture, not to predict maybe what happens next, but to see why that happens. That's very crucial to learn about that. Why the motion happens in that way. Huh? That's a good starting step. That's a kinematics, that's a dynamics, and two separate things in physics. Okay, in dynamics, your thought should be should be around three important things, which all those three things comes to in one classification. They call that Isaac Newton's law of motion. The first one, what is the first one? You have heard about that in Physics 11.
If F-net is there.
If what?
F-net is zero, so it will stop or stay in a constant will. Yeah.
That's great. Then when you talk about, let's say, for example, the first law of the motion in classical physics, because when you talk about the quantum physics, you see these things is going to be different. These things are completely different. Then you say that when in the first law, it means that if the total forces acting on a mass, for example this one, is going to be zero, which it means that the sigma, sorry, my sigma is like that. I hope that you get used to it.
So big.
That's right. Sigma f as a vector, I, which I starts from n, y1 goes to n, becomes zero, then in that case, it means that two things may happen. If the object is stationary with respect to a reference frame, it remains stationary. It means that it doesn't move. Yeah. Unless there's some kind of, yeah? But if it's moving, it keeps the way which it moves. What does it mean? For example, imagine that. I just bring a difference here. For example, the mug which I have for my tea. Oh no, it may fall down and break. Let me use a different thing, much safer. Look at that. Look at the pencil case.
Yeah.
It means that if the net force is zero, and this is stationary, it remains stationary. But imagine that if you are riding a bicycle, and if you are moving with a constant velocity, but imagine Jake is riding a bicycle, Sean comes to just want to make a joke, you try to push, let's say, Jake. In that case, Jake accelerates. Yeah. But if you do not put any forces there, Jake, yeah, that's right, Jake? Are you listening?
Yeah.
If you do not put any force, then J continues its movements without the acceleration. That's what it means. Then from the first equation of the motions, from the Newton equation of the motion, is if you want to make a call, you can just make a call. Then. Do you want to make a call or?
No, just
okay. Then the first equation means that it's necessary to look at the force as a vectors, and when you just want to analyze the dynamics of one scenario, you try to look at the force as a vectors and add or subtract the forces as a vector, not as a scalar.
Oh.
Does it make sense?
Yeah.
Huh? But I think at this stage, I'm just going to pause for 1 single second. And I'm just going to just ask you to look at something from the book, which is going to be, because I just wanted to just go to the second, I should say, the second law.
Yeah.
But before that, let me show you something. Before I just go to the second law, let me show you something. No, let me just tell you the second law, then I talk about this one, it makes more sense. The second law you have seen of Newton. What is that?
And then it's not there. So.
That's right. When you are acting forces on an object, in classical physics means that when you are exerting force on an object, stationary or moving, and these forces, they do not sum up to zero. Then these forces, the net of these forces, causes a motion in that particle direction when the force net is not zero. Huh? What do I mean? I mean that in simple law, you say that, okay, sigma F, let's say, I call that, for example, a direction. Let's call the direction X. Along the I, for example, this is going to be sigma Fi, which is the sum of all the forces along the X direction, causes what? Causes the mass of the object, the acceleration which it takes. Because I'm just net forces is along the X direction, then the acceleration you expect to just be produced along that particular direction. Then as a result, you can say, okay, can I just write the same equation if I have a two-dimensional motion? Let's say, okay, I have net force along the Y, I equals to 1 to N, produces acceleration along where? Along Y direction. Huh?
Mm. Oh, yeah.
That's right. These are two equations which we can derive from. You can have, if you have infinite dimensions, then you can just continue infinitely to write these equations, which essentially all means what? Essentially all means that if the net force along one particle direction is not zero, it produces acceleration along that direction. Huh? Then you have forces in many different directions. Then you have to do what? Then you have to do right. That's so true. Okay, let's do an example. I just wanted to use an example of a pendulum, of a clock, which, have you seen those old wall clocks? That there's a pendulum?
Yeah. Oh, yeah.
I just wanted to use that example, but I just keep that example when we talk about the gravity, because gravity plays a huge things on that. And then we are just gonna do an example. Probably it's gonna be for tomorrow. We're just gonna use the same equation of the motion, not the equation, the dynamics rules. Use the same pendulum. Do the experiments once on the Earth and once on the Mars planet to see how the time is going to be different in between these students. We're going to do that tomorrow.
So, sorry, I'll just 3 times the call.
Yeah, please, you can just answer.
Oh.
Okay, let's do an example.
Let
Let me just use a very conventional example, which on every textbook
you
you will see that.
Object.
You have seen that example on Physics 11, huh?
Yeah. Food.
Where's BK, by the way?
I don't know. Yeah, he probably today is a snow day.
That's right. Well, maybe it was a test day.
What? Test day.
Test.
What test? What? Test.
Limit. Calculus test.
Yeah. Oh gosh. You got it. Is that hard or not? Yeah.
It is extremely easy. Math and physics are easy.
You're gonna kill me.
Oh no.
Yeah, you put it out
Guys, give me 2 hours. I'm gonna grab a different colors. They come back in 2 hours. Okay. Try. What time is it now? We have half an hour, huh?
Yeah.
I think it's more than enough. By the way, do you know there's a Starbucks close by here?
Starbucks?
That's right.
No, I don't know.
No, close by?
Only it's Tim Hortons.
Tim, where's that?
Tim Hortons is over the gas station.
Gas station Esso there?
Yeah.
Ah, okay.
Oh, it's there, but?
Huh?
That way?
That's right.
Oh.
It's going to be a very good example. Tomorrow we continue with more challenging examples.
Oh, quantum harmony. What's that?
And 1,
And 2. And 2.
and 2. Okay.
Wow.
Okay, guys. Look at that. We're just gonna, let's call the angle which is created here alpha, and I know that they are perpendicular, and okay. Let's as a very quick example to explain how this equation works. Let's try that. Then after that we do something more challenging. Look at that. For this one, I'm going to also just use what? Kinematics or dynamics for that problem? What do you think?
Dynamic.
Dynamics. I can use also kinematics, but I'm not interested at this moment to see what is the position of the M2 after 2 seconds there.
What is the mass between M2 and M1?
What is the mass?
Yeah.
You mean this one?
No, M2 and M1. Which one is bigger? About the mass.
We just put M1 bigger because we need that. It just pulls the system down and causes the motion.
Yeah.
Because there's a friction between these two, then I assume that there is no friction between there. Then the system movements caused by the pulling of the mass M1 towards the gravity. And that's why I decided that. I say, okay, I'm just going to look at that. And I'm not, at this moment, I'm not interested to see how much movements M2 and M1 may make. I'm not going to make any prediction for time. Then I'm just going to analyze how the motion analyzes. That's right. Then I see that, okay, for these ones, I have the surface. I have, for example, in my things, I have, for example, one, let's say, for example, look at that. This is a tree. Everything is around there, and for example, that's a tree. But these are distractions. I just want to simply analyze the motions. What do? I say, okay, I'm just going to come. As you said, free body diagram. What is a free body diagram? Can you define it?
Analyze the forces.
Huh?
Analyze the forces acting on the object. Yeah. Acting on the object.
But why do you do the free body diagram?
To know how the motion. Yeah.
That's right. But also at the same time, you try, as I said to put the tree there. The reason is that you just want to isolate the one moving object and to see that object in isolation.
Yeah.
Huh?
Yeah.
And that's what you do there. For the mass M2, imagine that. For the mass M2, Let me just put that on, let's say. We know that this is M2. Let me put the reference frame like that. The motion is going to be this. I put Y, I put X. Huh? Does it make sense? Is it correct if I define my reference frame like that? Attached to...
Wait, one more time.
I thought that if the direction of the motion is going to be downwards, then I put the positive direction of the X along the direction of the movements. Then I said, okay, then the X positive is going to be pointing downwards. Does it make sense, guys?
Yeah. 是这样子的，我也是这样子的。
Yeah.
I do.
It makes sense to you? How about you, Sean?
Yeah, maybe makes sense.
Well, what is your suggestion then?
Yeah, it is perpendicular to the surface.
That's right. Or you have no idea about that. You do not know what is the direction of the motion. You can just put the X on the other direction. Then when you get the minus sign at the end, you notice that, okay, that minus sign can be interpreted as to make the opposite direction for the moving body then. Huh? That's right. Then that's what it means. I do not know what's the direction of the motion, but I know one thing. I know two things. The first thing which I know is that the reference frame, direction of the reference frame is completely arbitrary. It means that this is on your choice. We can just put it that way, this way, anywhere you want.
Random.
But the signs which you get at the end by using those formulas, it modifies your assumption. Initially, you have a prior, for example. You say, okay, at this stage, I assume the motion is going to be downwards.
So I think downwards.
Then I put the direction toward the X positive along the direction. But at the end, my results prove me if I'm right or wrong. If I get one minus sign from my force, it means that I had to just reverse the direction of the motion. Huh? Then that's your assumption. It's completely arbitrary. Okay, and now I just want to draw the forces. What is the first force I can draw?
Gravitational force.
Gravitational force.
Yeah.
Which means that it's going to be this one. It's going to be the perpendicular,
And
which is what? It is going to be
Earth.
M2G. Let me cut the tree, which I find.
The tree.
That's too much in the way. Okay, I have one thing there.
And normal force. And yeah, normal
Oh,
force.
why normal force?
Because it's perpendicular to the surface.
No, I do not see any normal force there. No, why normal force?
Why not?
Because I'm thirsty now. To get some work. Why do you see normal force there?
Because it's perpendicular to the surface. So
I say there cannot be a normal force unless. What is the third law of the motion? What is the third law of the Newtonian physics? The third law means
reflection or reaction.
for any action, there's a reaction.
Reaction. Yeah.
Okay, what is the normal force? Does it come from the third law from physics 11? You know, the normal force is a result of the third law. It means that the normal force, you kick something, it's like that. For example, I'm on the street, I kick someone, and someone doesn't stand to watch me. I'm kicking him. He kicks me back. Huh?
Yeah.
That's how you do it. You are not still kicking the surface. How you kick the surface? You have to decompose your vector. Look at that's a crucial word to use it.
Compose vector.
Decompose, that's right.
Oh.
Which is this,
And
which is this. The composition of the force. Here this is alpha. This is also alpha, huh? Am I right?
this is
Which one is alpha?
that one is alpha.
This is alpha.
Yeah,
This
that
is
one.
90
No,
minus alpha.
90 minus alpha. Yeah.
And that one becomes
That is
alpha. The other one.
Yeah, that.
The other one, which I just put it there, becomes 90 minus alpha becomes alpha itself. Then as a result, if this is alpha, what is this component of force?
Cosine alpha.
That's right, it becomes m2, let me just use my pen. It become, no, not this one. What time is it, guys? How much time do we have?
To 1 or 1 10. To 1 or 1 10.
Okay, thanks. It becomes m2.
Sorry? 15 minutes.
That's right. Then this component becomes how much? Because m2, the mass,
Yeah.
because this one, the total force was m2g, I decomposed that force with respect to the reference frame which I defined.
Exactly.
That's what I did. Huh? This is m2g times cosine of the angle between these two. And how about this one, the other one?
Sine alpha. M2G sine alpha.
That's right. m2, this is the mass of the moving object. G sine alpha. Alpha is this, and also is this.
Yeah.
Then I decomposed my total weight with respect to the reference frame which I proposed.
Proposed. And then have a friction.
That's right. No, we can include it. Let's see how far we can go. And now look at that. We talked about the normal force, and now that's the story. I kick someone and he kicks me back.
Yeah.
Now the normal force,
Cancel it all.
it becomes as
reverse of yeah.
That's right. The normal force becomes as an action on the surface, and then at surface, it seems you kick that surface, and the surface says, "Oh, you kick me," and it kicks you back. Oh, then that's going to be this one. Then you get the same force.
Super.
I call that F normal force, which is normal. Normal, you know what does it mean?
Yeah.
What does it mean?
No way.
Normal means
Yeah.
perpendicular.
Perpendicular.
That's right. Normal means perpendicular. Normal force is a force which is perpendicular
To the surface.
to the surface.
Yeah.
You mean this one? Huh? Okay. Now this one. The first object is now analyzed completely. Huh?
It also has tension force.
Tension.
Yeah. From
You mean this one?
M1, yeah.
That's right. Also, thanks for that. I almost forgot it myself. I thought I had done, which I'm not. And also you have something. Look at that. This is again the third law of the Newton. It says that this is pulling the object. It acts a force like that. I call that Ft. But at the same time, because of that, this one reacts back to this.
Yeah.
And it calls what?
Minus Ft.
Ft. Huh? That's right. Otherwise, if these two are not equal, then it means that the rope either gets contracted or gets loose and it breaks. Because the rope is fairly stable, it means that these two forces should be equal. Does it make sense?
Yeah, if the
Now, it seems that in isolation, when we look at that body as a free diagram, it had all those forces. And now I can say that, okay, I have two forces along two different directions. One direction is x,
Y is right. Yeah.
the other direction is y. And what do? I come to say this one. Okay, I'm just going to use this one, the first one. I said the net forces along the x produces acceleration along the x. If m is going to be constant, then I just write the net forces along the x, provided that as a priors, I know that the x positive is that direction. But it means that F m2, but it means that m2, which is the mass of that object, times gravity acceleration, sine alpha, alpha is the angle between these two surfaces, I'm writing first the net force. I'm just trying to find sigma F. all the positive direction, minus
ft
ft
equals to 0.
equals what? y0. I have no idea what's going to happen. But the thing which I say that is that, okay, I'm just going to sum all the forces along the x.
Yeah.
Which direction shows the x?
Downward.
Which direction shows the x? As a prior, I assume that x is going to be that direction. Then m2g sine alpha is one force. Another force along the x is going to be ft. Ft is pointing towards a negative direction because that's a positive. Then it becomes minus ft. Is there any other forces along the x for this object?
Friction.
Friction? Yes, we can include friction. I call friction is going to be what?
ff.
I'm just going to do that, the friction there. I put F. Okay, minus. Let's do not use the friction at this stage because it makes it more complicated. Let's assume there is no friction. There is no friction because I just want to use as a demonstration how this equation works, not to make it more complicated then. F of t becomes what? No other forces along the x direction. Then it becomes m times acceleration along the x.
Yes.
Huh?
Exactly.
This is going to be my first equation. If you had the friction, you could have seen that minus ft minus ff equals max.
Yeah, and then the y-axis.
That's right. This is one question. And also, you have what? Y-axis. For y-axis, what you say?
G cosine alpha equals to minus f n equals to ma. What?
You were very smart, you just jumped ahead. But let's write the equation first. We say the net forces along the y becomes, which direction is positive? This one is positive. Fn is towards the positive. Then it means Fn
is positive.
Minus, this is pointing downwards. It's going to be negative.
Equals to 0.
M2g sine alpha equals, I have no idea if there is no motion.
Cosine alpha, not sine.
Oh yes, sorry. Cosine alpha equals what?
MAY.
That's right, because I do not know if there is a motion. But you cannot see that. We can prove there is no motion. MAY. This is the first set of the equation of free body diagram of this object there.
Yeah.
Huh?
Yeah.
Equation 1, equation 2. Okay. Let's drink some water.
Simplify it.
It's too early to simplify because we have two objects.
No. And I move on.
We have also this object. We have to write the same free body diagram equations for this.
Okay, and then we have.
What is the requirement for the free body diagram? First of all, I'm going to attach the reference frame to this. I'm going to say, okay, I assume as a prior that the direction of the motion is going to be downwards. Then I say, okay, that direction I call it x, and I call this y. Because I assume as a prior, it's pulling down due to gravity, then that direction of the motion represents the positive direction of my reference frame.
M2.
That's right.
Yeah.
Then how do I write the equation? I have only one force, it seems.
Tension force. And tension force.
That's right. I call that
M.
W. Oh my God, these markers are useless. W equals M1G.
M1G.
That's right. M1G. And there's also, because it's being pulled up by the rope, I call that also, there is one other force.
Friction. No friction.
No friction.
You know everything.
FT.
Tension.
Tension. That's right. And FT from there. But if the rope was being contracted or was getting loose to get to the point that it's getting detached, then these two forces are not equal. Huh? At this stage, I'm just going to write the same sets of equations for these objects. Okay, the set sets. Net forces along the x becomes what?
0.
There is no force along the x.
0.
F along the x equals 0. No force. Let's pull that conclusion number 3.
4.
How about this one? All the net forces along the y becomes what? Along the y. How many forces do we have?
2 forces.
2 forces. Which one is positive?
M1G.
That's right. M1 G minus Ft equals to
M1. Yeah.
y. And M2, it has to become M1. M1, and this was supposed to be what? M2. I forgot to put the indices of the mass. M2y. Let's put that equation number 4. Okay. How much time do we have? 14 minutes.
5 to 1.
Okay, nice, thanks. Look at that. We have 4 equations there, and now it seems that we are still nowhere.
What?
We are still nowhere. We haven't done anything yet.
Yeah.
Because still we are looking for what is the direction of the motion, what is the acceleration that the objects are pulling down or pulled up. Huh? Then you're looking at the equations there, 1, 2, 3, 4. What do you think, guys? This equation number 3, it's a useless piece of information there, because it's good to know that along the x in that direction is 0, but what else can we do?
Yeah, well, nothing else.
That's right. But look at that, guys.
Yeah.
I have okay. This one, if we assume that there is no movements along the y, then you can simply deduce that ay equals to 0.
So m equals to 0.
That's right. There is no motion along that. Then it means that what? Then it means that this right equation becomes 0. Then it means what? Normal force equals to
0.
m2g
Equals to
cosine alpha. No, it shouldn't be 0, because this right equation becomes 0. Then this means equals, this is this one. These two should be equal, that the net becomes 0. Okay, that's kind of the first result which we get.
Oh, yeah.
Huh?
Yeah.
You're almost done. If we do not even know that there is, this is the assumption which we make to simplify the equation. If we do not know there is a motion, we are almost done. We have all the equations that describe the acceleration. From this one, I just got Fn. Okay. And also for this one, we have m2g sine alpha minus ft equals m2ax, which describes the acceleration of that object along the x direction. If it's positive, it means that it's pulling down. If it's negative, it means that it should be pulled down. Huh? How do you get there? How do you get the a of x? That's the question. Because the question is that, are you with me?
Yes.
Are you tired? Do you need a 2 minutes break?
No.
You're fine? Look at that. The most important piece of information is right now in front of your eyes. Because you see that a of x represents what? It represents that moving object. And now you're trying to find what is a of x. Sean, listen, it's very important. If a of x, which you get, is positive, it means that your prior assumption that the object is moving towards that direction is correct.
Yeah.
If a of x is negative, it means that, oh my God, my assumption, my prior was not well established. It seems that I was wrong because the object is being pulled up.
Yeah.
Then that information, this equation number 1 is the most piece of information which you can obtain. But how to get the a of x? In order to get a of x, what do you do? So I'm just going to write it on top, okay?
Yeah, of course.
The A of x is what? The A of x
Equals to G sine alpha.
means M2.
G sine alpha. Minus FT.
That's a simple algebra, huh? Minus FT divided by what?
M2.
M2. I didn't do any physics there. There is no physics there because all I did, I divided both sides of that equality by M2 to get the A of x as a vector, huh?
Yes.
But what is M2? The mass, which we know how much is that.
Yes.
It's 5 kilograms, for example. The G is now universal constant. The sine alpha, I know because I know how much is the alpha, maybe 30 degrees.
Yeah, 30.
And F of T,
We don't know yet.
I don't know.
Yeah.
That makes it messy. And also M2, I know what is that because I know the mass.
Yeah, we know
So-
the math.
That's right. I know the mass. But the thing which I do not know, it's a kind of a mysterious thing, is going to be the tension force. But can I get it or no? From that equation, I have the normal force. No tension force. I know the normal force is going to be equal to that component.
How about another one?
But number 3 is a piece of useless information. It cannot be helped. But number 4,
It works. It works.
Yeah.
that's right.
F equals to M1G minus M1A1.
And equation number 4, look at that. It sounds a little, I should say, obtrusive. How to get that? I should say, can you just get Ft from that equation?
Ft equals to G over A1.
Ft equals to what?
G over A1.
M1 G plus AY. Huh? I simply factor this. I took
minus,
F of minus AY.
Yes.
That's right. But what is, I should say, what is AY there?
MG
Equal
equal to G. No. Yes, it's equal to G, probably. The permutation of course.
My is equal to G.
Yeah.
What? It means that if we put it equal to G,
Ft equals to
we do not get the right answer because AY, it may be, it equals to G, it means that it's being like the free fall.
Yeah,
Oh.
no
And it's
rope.
not a free
It has a
fall.
rope.
That's right, there is a rope. If you cut it,
Yeah.
then AY
Then
becomes
you-
G because it becomes like a free fall.
Yeah.
Huh? But it cannot be as a G because in that case, it seems that the system is broken. It falls down there.
So
Then you have a feel like that.
you
But now we are faced with the question, how can we just get the AY from that equation?
No.
Huh?
No idea.
To plug it there.
But those fishes. Yeah. Sure.
Yeah, that's a problem. Because look at that, you can simply write A of x. It's equal to, let's say, G sine alpha minus
minus Ft over M2.
M1
M1.
over M2. I simply plug a figure, divided both sides by M2,
Yes.
times what? G minus
AY.
AY. But it seems that something is tricky. Because we were looking for the A of x, we got the expression of the A of y, we still did not know what is A of y.
Yeah.
Huh? I say, for example, I say how much you earn. You say 2 times of how much Jake A makes. How much Jake makes. That's a problem. And now that's a problem. We have to make some kind of modification on the problem which we have. But what do you think of that scenario? What is the solution to get A of y? We can just make a simple modification to resolve the situation, find a clear-cut answer for f of t,
How?
then put f of t there to just get rid of the A of y.
How?
I just want to leave that for you as a food for your thought. You come back tomorrow, I'm not going to erase this word.
Oh,
You
gosh.
come with a good, I should say, assumption that you can solve this problem to get the A of y in terms of that, it's not a free fall. It's not going to be G, it's not a free fall. But how make this modified that we do not get the A of y in terms of the A of x? Huh? Okay. Please think of it. The board is going to be revealed like that. Tomorrow, when we start, we're just going to talk about that and have more advanced problems. And you come with your solution that how these things is going to be worked out. What time is it? 5? You're done then.
Yeah.
Yeah, definitely think of it. Tomorrow, come with your answers, how to resolve that issue. And hopefully by end of next week, we can just have a quick, I should say, test on chapter 1 then. By
Tomorrow?
Friday. No, by Friday. Yes.
Friday, yeah.
That's right.
Ooh. So we'll be. I don't know how to say that. So I just asked.
Calculus class 1.
Yeah. If some student didn't come to calculus class,
Unfortunately, they missed the mark for the test.
Wow.
That's right. So it's going to be a very easy test. I think they come to the class and see how easy the test was. They should be surprised and say, oh my
Can
God.
I get a full mark on that?
Full mark on the calculus test.
Yes.
No way.
Sure, why not? But you're not going to use it anywhere. Okay, guys, thank you very much for your participation.
Of course.
It was a great class.